We were talking about performance-based design. And I told you that in performance-based design, we satisfy some performance objective. Performance objectives are function of a performance level and hazard. Performance levels are representing the extent of damage and hazard levels are representing severity of ground shaking. So we are classifying that at what level of severity of ground shaking, what extent of damage is acceptable to us. Okay, and we will design our structure in such a way that we are able to restrict the damage to that extent which we have targeted at the given intensity of shaking. So we will take up now these one by one. First we will talk about hazard and hazard levels. So when we say hazard here, I mean seismic hazard, earthquake hazard. You have heard this term? Okay, all of you? Hazard, earthquake hazard, seismic hazard. Can you define me what is meant by seismic hazard? When we say hazard, what does it mean? If I ask you to define hazard, how much is the seismic hazard in Roorkee? What will you say? What would be your answer? What is hazard? Yes? All of you have heard this earlier.
So hazard is a probable event which is posing risk to life and property.
So probable event, in this case I have already given seismic. That event is earthquake. So is hazard earthquake? I am asking you earthquake hazard. How much is earthquake hazard?
Vulnerability of any structures to seismic event in a particular zone.
So suppose there is no structure, there will not be any hazard?
Yes.
Since we are focusing on the structures and seismic events,
My question is very simple. How much is seismic hazard at a site? Let us say Roorkee. Suppose there was no structure in Roorkee, Roorkee was barren land. Will there be hazard or not?
Yes. 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 There will be so.
Hazard just means
So what is hazard then?
extent of damage. Extent of damage.
Sorry?
Extent of damage.
Extent of damage to whom? There is no structure. So extent of damage in what? In fact, I have already written, if you would have noticed. What is hazard? Severity of ground shaking. How severely the ground is going to shake at a site. It has nothing to do whether structure is there or not. Ground will shake even if the structure is there or not. What you are talking about is risk. If there is no structure, let the ground shake with any level of severity. How does it matter to me? Its effect will be there when structure is there. Okay, but that doesn't mean that the ground will not shake if the structure is not there. So the severity or level of ground shaking is hazard. Okay. Some people also answer that hazard is probability of occurrence. You might have heard this also. So hazard is probability of occurrence. Hazard is not probability. Hazard is level of shaking. And if you have to measure level of shaking, in what units you are going to measure it? Okay, so this may be measured. So hazard is nothing but intensity of ground shaking. Ground shaking intensity. You can measure acceleration. You can measure velocity. You can also measure displacement. All three are representing intensity of shaking. If you are measuring accelerations, the units will be meter per second square or G or Gal. What is Gal? 1 centimeter per second square. Okay, so centimeter per second. Velocity, meter per second, and displacement. So these are the different units which we use to determine the hazard. Okay. Well, for measuring acceleration and velocity, you need some instrument. What is the instrument used for acceleration measurement? Accelegraph or accelerometer. For velocity, seismometer. For displacement, which instrument you use to measure displacement? Is there any displacement pickup? Have you heard this term? Or you have invented this now? Displacement pickup. What is a displacement pickup? Acceleration pickup is there. But what is displacement pickup? Any instrument you know which can measure the displacement during earthquake? No such instrument. Okay. So how we obtain displacement? Actually, we measure the ground acceleration. We represent it by UG double dot. Okay. Then we measure this acceleration. Peak value of this. Okay. This we call EGA. Peak ground acceleration. So this is coming from accelerometer. We can measure velocity, with time. This is coming from seismometer. We don't have any instrument to measure UG. This can be measured, this can be obtained from integration of velocity. Okay, velocity you can either measure directly using a seismograph, but most of the cases it is also obtained from integration of acceleration. So there is a term called strong motion. Have you heard this term, strong motion? What is a strong motion? So we have a strong motion accelegraph. Strong motion is measured using an accelegraph. Seismograph is usually used for measuring. This is more sensitive, but at the same time its range is less. So it can be used to measure weak motion. Strong motion, which is affecting our structure, which is capable of damaging our structures. That we call a strong motion. And for that, the instrument uses accelerogram. So we get a record of acceleration. The record is called accelerogram. So this is accelerogram of an earthquake. And accelerogram of an earthquake is like signature of earthquake. Unique. So it is signature of an earthquake. It is unique. Strong motion we measure using acceleration. Weak motion we measure using seismogram. Okay. And velocity we can obtain by integrating acceleration, and displacement we can get by integrating it further. Direct measurement of displacement so far is not possible. People are trying now using satellites, because for measuring displacement we need a datum, a reference point. So when the whole earth is moving or a large portion of the earth is moving, you don't have that reference. Reference can be in space. So satellite can provide you that reference. Using GPS, you can try to measure the displacement. So far, the displacement is not measured. Measurement is done mostly of acceleration, in some cases velocity also. Okay. Now, when these instruments were not there, then how the intensity was measured? Accelerographs are being used for the last 60 years. Around 1950, people started using them. But earthquakes are coming before that. There are records of earthquake, historical records of earthquake. So at that time, how the people were quantifying intensity of shaking? Yes? There was no instrument by which you can measure acceleration or velocity based on the damage. Okay, so before the instruments were there, the intensity was measured using what we call subjective scales. Pre-instrumental error. Now also, you can't put instruments everywhere. Okay? So, still, we use those. Wherever the instruments are not available, there we use intensity scales. How you can use intensity scales? Every person himself or herself is a sensor. In our body there is a sensor. Which of these three values our sensor can record? Acceleration, velocity or displacement? Displacement? What our sensor is sensitive to? Human sensor. Displacement? Acceleration? And then third is velocity. Out of the three, which one we are sensitive? Suppose our sensor was sensitive to velocity. Then Earth is moving with a constant velocity. We would have sensed that, but we don't sense that. That's how our evolution has occurred. So we are not sensitive to velocity. And when we are not sensitive to velocity, we can't be sensitive to displacement. Okay? If you are moving on you are sitting in any vehicle where there is no acceleration, it is moving smoothly, you can't sense it. If you are sitting in a train which is moving very smoothly, or you are flying in a plane, you do not know that you have moved so many kilometers. So our sensor does not work on acceleration, our sensor does not work on velocity. Our sensor does not work on displacement and velocity, it works only on acceleration. So our sensor is sensitive to acceleration. Whenever there is an acceleration, okay, then we can sense. So human being is a sensor. So people were using humans to define earthquake. What type of shaking, whether it was perceived or not. If it was perceived, was it severe? Were people frightened? Did they run out? Depending on what level of shaking is, your reaction will be there. So if your perception, the shaking is low, you will sense yeah, something is happening, okay, but you will not run. But if real earthquake shaking is occurring, the natural tendency will be there, natural instinct will be there that you will run. Okay, so human being is the sensor, then all our structures, they are sensor. Damage to a structure will depend on intensity, but damage to different structures will be different at the same intensity. That's the problem. So these were based on observed damage. So whatever structures were there, people observed damage. But different people looking at the same damage, because it is subjective, it is human observation of the damage. So human observation of the damage may be different. Some people may think that this damage is too much. Some people may think that no, it is less. So to minimize the subjectivity as much as possible, subjectivity cannot be totally ruled out because it is based on human observation. But to minimize that, there were standard systems. Of quantification. These are called intensity scales. Some of the intensity scales you may be knowing. MSK, okay, MMI, European microseismic, European macros. So there is a European scale, there is a Japanese scale, okay. Number of scales are there. You can just Google and write this, or you can write this in any seismology book. Okay. Number of such scales are there. So they have tried to standardize that if different people are observing the damage, they should come to the same level. Okay. So for that, the buildings are classified into different categories.
Sir, it's EMS 98.
EMS, European macro seismic intensity. Classes of buildings or structures. You have A, B, C, etc. So maybe A may be the weakest type of buildings. The dry stone or mud or random rubble masonry buildings, those can be A. Slightly better buildings, like we have brick buildings, those can be B. Okay. If we have brick masonry buildings in cement mortar, that may be C, and so on. So like that, there is a classification of the building, and then there is a classification of damage. Classification of damage is done in grade. Grade 1, 2, 3, so on. So, grade of damage is related with the type of the building and then the intensity of this. So, let us say intensity 6. So, intensity 6 means that there will be grade 1 damage in A class building, whereas the other buildings will be damaged. Okay. Up to grade 5, up to intensity level 5, it can, there is no damage. It can be sensed by human beings, let us say grade 4 or intensity scale 4. Okay. Below that, it can't be even sensed, but still, there may be some shaking which may be recorded by some student. So like that, The grade of damage and classes of the buildings, those are related in intensity scales. So this is done so that different people come out with the same level of intensity. So after an earthquake, whenever an earthquake occurs, let us say in our country or anywhere, teams go to different areas, and what they do, they try to record the damage. And when they are recording the damage, they are recording in which class of the building, what type of damage is occurring in that. So class of building with the grade of the damage. Then they can come out with the intensity scale. And that's how different teams which have visited, they come out with more or less same intensity measurement or same quantification of intensity in a particular area. Okay, so this method is used to quantify intensity when we do not have instruments. If instrument is there, then that is a better measure of intensity, where you can measure the velocity or acceleration directly. That is a more scientific measure. Okay, because if you have put different instruments in the same location, all the instruments will give you the same level. So there this subjectivity is not there. So that's why the modern method is instrumented method. Wherever instruments are not available, because now also we have not put instruments everywhere in the country or everywhere in the world. Some countries, they have very dense network of instruments like Japan, Taiwan, western coast of America. So they are very dense. In our country, we do not have that dense network of instruments. Instruments are sparsely located. So in between the instruments, we have to still depend on the subjective quantification of intensity. Okay. Now, earthquake is a rare phenomenon. Smaller earthquakes are more frequent. Larger or damaging earthquakes is it good or bad? First of all, earthquakes are rare. Should we be happy about it? Or it's not good, you think? Earthquake should come as well.
So not every day we should have ample amount of earthquake so that we can record when it takes something down. So that helps in prediction. And we don't have too much data for earthquake.
So you want your data and people should die because you want your data. That's why you want that earthquake should come more frequently.
But if your earthquakes are more frequent, then we will take better precautions because we have an idea of
Right.
what's happening.
What is acceleration due to gravity? That is also an acceleration. Earthquake shaking is also an acceleration. Acceleration due to gravity is also acceleration in vertical direction. In vertical direction, 1g acceleration is always acting. So earthquake is also an acceleration. So if earthquake acceleration was also like gravity, all our structures we will always design earthquake resistant. The problem is that these earthquakes are very rare. When damage occurs due to an earthquake, we try to understand. And the problem is that human memory is very short. We tend to forget it. Okay. We believe that now it will not. And we become complacent in construction of our houses, our buildings, our structures. So our structures are not earthquake resistant, earthquake safe. If earthquakes were coming every day, automatically or till now, everybody would have known how to construct structures from the experience itself without doing MTech in earthquake engineering. They will know how to construct structures. Because we have a feeling when even a mistri is constructing house without any calculation and this, he has a feeling that under gravity for this span how much beam you require. But that feeling is not there in case of earthquake. Because earthquake is not part of our day-to-day life. Okay. So our brain is not trained for that. But gravity, our brain is trained. So even without calculation, many times we can say this being will survive or this being will not survive. So at least some idea our brain has.
So
So
this is similar to like in the northeast, on the banks of the rivers, people construct houses with wooden houses because they are habituated with the floods, like on East River and all. They construct wooden houses beforehand.
right.
Because
So wherever any phenomena is frequent, people get used to it. They learn the lessons and then take precautions. Problem is that our earthquake is very rare, especially the damaging earthquakes are rare, and the people tend to fall. That's the problem. So if I plot this relationship, let us say on one side I take intensity and another side I take probability of occurrence. Okay, it is something like this. The large intensity earthquake probability is less. A smaller intensity earthquakes, the probability is large. So at any site, a small probability earthquake, very small intensity earthquakes are occurring on daily or weekly basis. Every day, some very small earthquakes occur. Okay, earthquakes of magnitude -1, -2. What does that mean? Earthquake of magnitude -1. Can magnitude of earthquake be minus? Anybody heard earthquake of magnitude -1? Magnitude scale is a logarithmic scale. Okay? So when we are talking about magnitude, you should be clear, one is magnitude and another is intensity. Hazard, we are representing in terms of intensity, not magnitude. What is the difference between magnitude and intensity? How do we measure magnitude of an earthquake? In which units? Which scale? Intensity, just now you said that it can be measured in G, meter per second square, or Cal, or meter per second. How the magnitude is measured? Magnitude of a scale, earthquake? Richter scale. The most commonly used Richter. This is represented by ml. We can have moment magnitude, okay, surface wave magnitude, and so on. So these are some numbers. Anybody know what is Richter scale magnitude? What it is representing? How the Richter scale is measured? We put a standard seismograph. What is a standard seismograph? A Wood-Anderson seismograph having standard damping. I do not remember how much is damping, you can just look. So it has a standard damping and it is put exactly at 100 km from the epicenter. Then we will get this trace Seismograph, what trace it is going to give us? Velocity. Seismograph. We take that trace, okay, and we take its log to the base 10. So that log value is mm. So you hear magnitude, Richter magnitude 8, 7, 6, 9. So what does that mean? That trace, okay, that trace is in microns. So that trace to the base log, or log of that trace to the base 10, that is magnitude. Other scales are also logarithmic scales. Okay, so logarithmic scale means 0 value doesn't mean that it is 0. 0 value means it is 1. Minus means 0.1. So minus scale is also possible. So magnitude -1, -2 are also possible. Only thing it means is that very small amount of energy is released. So magnitude is representing the total amount of energy released. Intensity is shaking caused by that energy at some place away from that epicenter. Okay. So you can ask me, have we placed these Wood Anderson accelerographs or Wood Anderson seismographs at 100 km from each epicenter? How do we get it? Because once the earthquake is there, immediately you will get a news that magnitude 7.3 earthquake has occurred at this and this site. How do they know?
Interpolation.
Interpolation of what?
Maybe there is a seismograph at 200 kilometers at 400 kilometers. So they interpolate the values at 100 kilometers and say that.
And how they know the epicenter? First of all, for interpolation, you need to know the epicenter from your instrument. So you have to understand, throughout the world and within our country, there are different measuring stations. Seismographs, accelerographs are placed at different locations. Okay, and you can get a record. From that record, first thing you have to do is you have to locate the epicenter. How the epicenter is recorded is obtained if you look in to the plot of UG double dot. This plot is something like this. So initial, there is an initial portion which represents P wave. And then from here it is S. What is P wave and S wave?
P wave travels along the way, like disturbance is along the way.
First of all, these are elastic waves. Compared to elastic waves, there are electromagnetic waves. You know what is the difference between these two? Elastic waves and electromagnetic waves?
So elastic waves require some medium to travel. Electromagnetic waves require not necessarily required.
Not necessarily, but they may require.
They can travel within medium. Elastic waves are
So what is the basic difference between them? And first of all, example. What is the example of electromagnetic wave? Light. Okay. X-ray. All these are infrared wave. Okay. Ultraviolet. All these are electromagnetic waves. Electromagnetic waves can travel in vacuum. Okay. These can travel in some medium also, but in mediums these get dissipated very fast. Okay. If it is a dense medium, let us say even a thin layer of steel plate, light can pass. Okay. Some other frequencies can pass, but to different times. So electromagnetic waves can travel very long distances in vacuum. Okay, in space where vacuum is there. It continues, it doesn't get dissipated. It continues from one place and it goes. Dissipation occurs only because of its spreading, because that energy is being spread in larger and larger area. Okay, but when it hits a material, then it gets dissipated very fast. Elastic waves, on the other hand, these travel through vibration of particles in that medium. So the particles are vibrating. When I am talking to you, this is elastic. The sound waves are elastic waves, which are starting from my mouth, going to your ear through vibration of air particles. So air particles are vibrating, air particles are not moving, but the energy is moving. Particles vibrate, these transfer energy to the adjacent particles, and that's how the wave propagates. So this requires medium. Earthquake waves are also elastic waves. Those are passing through a medium. Okay. Now two types of motions of this medium are possible. In one case, if the wave is traveling like that, the particle motion is also in the same direction. Particle motion is vibratory. Particle is not moving along with the wave. It is vibratory, but the direction is same. This we call P wave. Other possibility is that the particles are vibrating perpendicular to the motion. This is S wave or second wave. Now, what type of wave is sound wave? When I am talking to you, the waves are traveling. What type of motion the particles are having? So it is compression and rarefaction. Compression and rarefaction. So the motion of the particle is in the direction of the propagation of the wave. Okay, so this is like free wave. But in case of an elastic wave, can air shear waves or S waves propagate? Why not?
Because it doesn't have shear strength.
Shear strength, partially. Why do you need strength?
Stress, sorry,
It does not have shear stiffness. Okay, it has compressional stiffness. If you take air and a volume of air and try to compress, it provides resistance. But if you take air and try to slide it like this, there is no resistance. So it does not have any shear stiffness. So the vibration of the particles, if you push a particle in this direction, why does it come back? Because of the stiffness. Because that stiffness is not there, it will not come back. So vibrations perpendicular to the wave propagation are not possible in air. But in solids, those are possible. So earth crust, when the earthquake waves are traveling, both types of motion are possible. Okay. So P waves require compression and tension of the medium. Okay. Which property of the material is coming into picture? Which modulus is coming into picture? In short, the velocity of P waves you can write down as square root E by V, and velocity of secondary waves, or we also call these as shear waves, that is square root G by rho. Because in primary waves, okay, compression and tension is available. So that is stiffness in compression of any element is EA by L. And when you are talking about the material per unit volume, it will depend upon E value. So compressional wave velocity will depend upon E, the shear wave velocity will depend on G. Which is higher for a material, E or G? What is the relationship between G and E?
E upon 1 plus 2, 1 upon E upon 2, 1 plus 2.
Okay, so you can see that the G will be less than half of it. So shear wave velocity is going to be smaller than primary wave. And that's why the primary waves at a location will reach first and then second. Okay. And how much this time gap will be there. That will depend upon the distance and the difference in the velocities. So this delta t, this will be equal to the distance L times Vp minus V1. You get it? So farther we are from the epicenter, more time difference between P and arrival of P and S waves will be there. So if you have recorded motion at any point, you can determine how far the epicenter is from that point. But you do not know in which direction. Whether it is in this direction 100 km, this direction 100 km, or this direction 100 km, that you know. So what we can do is, let us say I have these three stations. I will determine the distance from this station. I can draw a circle with that distance which I have recorded here based on the difference between P and S waves. Then I can take another, I can measure the distance here and I can, let us say, R2, and then I take from this point, let us say this is R3. So here I know that this is my where these are intersecting. Generally, this intersection will not be at a point. Okay, it will be a small area. I can precisely fix this if I have more number of such stations. Then I can do it from there also. I have another from here. So more number of measurements are available. More precisely, I can locate that. So now there is a network. Two networks we commonly use. One is USGS, American Geological Society, and another is in India, IMD, Indian Meteorological Department. So IMD network is there. So IMD declares the epicenter, and similarly USGS declares the epicenter. Sometimes that epicenter, there is a difference in those epicenters. The reason is because both are using different networks. So some numerical error, calibration error may be there. Okay. Once the epicenter is known and you know the distance, now you can do interpolation to determine what would have been the trace at 100 kilometers. And then you can calculate the return. So this is representing, this is one value for an earthquake. Intensity will be different at different points. So intensity depends on site. And this is for earthquake. For a given earthquake, there will be only one magnitude, but there will be several intensities. Intensity will vary from place to place. For us, when we are talking about hazard, we are talking about intensity. We need intensity, not the magnitude. For us, intensity is important. Magnitude is important because intensity depends on magnitude. But we are not using magnitude directly. We need intensity. The EGA, the acceleration occurring at my site, because the response of my structure will depend on intensity. Okay, and this curve, because smaller magnitude earthquakes, which will cause small intensity at my site, are more frequent. So the probability is more. Larger earthquakes, which will have larger intensity at my site, the probability is less. So this plot is something like this, and this we call hazard curve at a site. So at a site, we get a hazard curve. Okay? So larger intensity has lower probability. Okay. Smaller intensity has larger probability. So that means hazard quantity at a site is not unique. But depends on probability. Okay. So based on probability, so it will depend on the probability of occurrence or return period. The probability of occurrence can be represented in terms of return period also. So generally what we do, we take probability of occurrence or accidents in 50 years, then we can have a corresponding return period. And we call it level of. So we may have 50% probability of occurrence in 50 years. Why in 50 years? Generally, the design life of the structure is considered to be 50 years. In case of bridges, ASCO takes in 75 years. Because the design life of the bridges is longer, they are considering it 75. So if you know in 50 years, you can easily extrapolate it in any number of years you want. So the probability of occurrence, let us say 50% in 50 years. Return period, average return period is 75 years. Such an earthquake, such level of earthquake, we call serviceability earthquake. In short, we write SE. %50 probability means there are 50-50 chances. So that means one such earthquake is expected to occur during the lifespan of my structure. So if it is sure to occur, almost sure, then probability nothing is sure. But if there are good chances that this earthquake is going to occur, what will I do in my design? I will design my structure not to be affected. Its serviceability, it should continue to serve its purpose. So that's why it is called serviceability. Then the next higher level is 10%, more rare, 10% probability of occurrence. The return period, average return period is 475 years, and this earthquake we call design basis earthquake. Historically, world over, the structures are being designed for this level of. So that's why we call the design basis. Then we have 5% probability of accidents in 50 years. The corresponding return period is 1000 years. Okay, and this level of earthquake we call maximum earthquake. Some people thought that this is sort of maximum earthquake which we can consider in our design. But later on this concept changed, and currently what we are using is 2% probability of occurrence. The return period is 2500 years, and this we call maximum considered earthquake. And okay. So relationship between these different earthquakes. Okay, the PGA of BB, how much it is in terms of serviceability earthquakes, okay, that varies from site to site. It is not constant, okay, but there is a range. So roughly, the PGA at DBE is approximately 1.5 times PGA at serviceability. And PGA at MCE is roughly 1.52 times PGA at DBE. Okay, I will give you in tomorrow's class a more exact relationship, how we can relate at this side. But roughly, this is the relationship. In our code, the relationship assumed is 2. So that's why in calculation of AH, we are using Z by 2 into I. So that by 2 we are doing is to convert that to dB. From MC to dB converting. Okay, Z is not MC. I will talk about that again. What Z is representing, we will talk tomorrow. But this relationship in American code, they are using something like 2 by 3 Z. So they are assuming the relationship between dB and MC as 1.5. We are using 2. Okay. This relationship, as I told, will vary from place to place, from site. It is not constant, but range is there. It is not going to be 10 times. It will be in this way. Okay. So I think we will stop here, and when we meet tomorrow, we will continue from here. Sir? Yes. Any question?
Sir, how is it possible to have different intensity at
Sorry, how?
How is it possible to have different intensities at the same site for the same amount?
Different intensity at the same site. At a given site, intensity due to a given earthquake will be same. But our observation, our measurement may be different. 2 people are observing. You are also observing, I am also observing. Okay. But we are not measuring it. If we are measuring using an instrument and instrument has no error, then both of us will give the same value. So if we are measuring the intensity in terms of, let us say, PGA or some other instrumented quantity, then it will be unique. Because ground shaking is unique. Ground cannot shake in 2 ways. So ground shaking is unique. But if we are not having instrument, we are trying to judge from the damage to the structure, then our judgment may be different. So that difference comes because of the judgment, not because the intensity is different.
But when we draw the hazard curve, it is that curve is not on the basis of different earthquakes on that side.
Yes. So this curve, when I have plotted this hazard curve here, It is not representing single earthquake. At one site, even from one source, different earthquakes can come. It is not that on one source only one earthquake will occur. Smaller earthquakes on the same source are occurring frequently. Larger earthquakes are occurring rarely. Then there can be another source. There also some earthquakes are occurring. Smaller earthquakes more frequently, larger earthquakes. So this is sum total of all those. So if I consider the final effect at a site, that will be like this. That either this earthquake, this source can cause or that source can cause. So smaller intensity, larger chances, larger events will be occurring of a smaller intensity. Larger intensity, fewer events will be occurring. Okay. Any other question? Yeah.
Sir, when we talk about design basis earthquake, told certain period is of 500 years.
For certain period of 475 or roughly 500.
But we don't have the data of 500 years back. One earthquake has been, because certain period is 475 years. So then why we designing on the basis of the?
I told you that historically we have been designing like that, and it has been observed that if you design for that, even a large earthquake like MC, our earthquake will survive without color. This has been observed in the past. Because design cannot wait till you understand everything. Okay, Empire State design was done when mechanics was not understood. Still they design. So new design methodologies, new materials are coming. Not everything is understood. Still people construct it. So they learn from their experience. So what was learned from the experience that if they are designing for this, they were not even calling it DB. They were designing for a level which they were not calling DB. They were saying that we are designing for this. And when they were designing for that, the building was surviving larger earthquakes. So that's how this DB. Now we have quantified that and called it that this is DB. Earlier they were not calling it DB. The DB terminology is post 2000 in our country. Before 2000, there was no DB, no MC. Okay, just a label was given that to design for it. Okay. Any other doubt? Okay then, we will continue tomorrow.